Hi. So just a reminder, we've got a week and a day for our next exam. We are a little bit behind, so some of the examples in the guided notes might have to be skipped just so we can get back to where we need to be. So hopefully that's not too much of an issue. I can write down the answers and you can try to practice those. But also the homework, I think, is sufficient practice for most things too. Just in case we don't get to cover all examples, just wanted to give you a heads up. Are there any questions on the homework? All right. Well, we'll finish 8.4 today. And we were looking at trig substitutions in 8.4. So example 5 and 6 are somewhat similar. So for the sake of time, we'll skip example 5 and look at example 6. You should have the answer come out to be the natural log, if you're working these, of course, x over 9 plus the square root of x squared minus 81 all over 9. And this one here, we could apply the same trick we applied in example 4, where we could add what's inside the absolute value and then use properties of logarithms to simplify that. So remember how we turned that into a difference, the numerator and denominator, and then this, the ln of 9 would get absorbed into that constant. What?
No.
So we could just call this another constant. This, call it, I don't know, C1. So that's bare minimum, we can have that. Yeah, if you don't like that, don't do it. It's not crucial. All right, so that example is similar to example 6. This example, you should end up coming up with an integral in terms of theta, and you should be finding the antiderivative of secant theta. It's similar to this example, so we'll work this one instead. So slightly different approach if you're using the textbooks method, but it still all comes out as the same. And what we've been doing is we've been taking, we've wanted a square minus 1 or a square plus 1. So we would factor this 81 out of the y squared minus 81 and then take the square root of it. So we'll take that out. Is everybody okay with that at this phase? So we have that. So that's what we're doing here. Just preparing that for trig substitution. All right. So what should our trig substitution be? Secant? Do y'all agree? Should that be secant? Yeah, because secant, if y over 9 is secant, then that's secant squared minus 1, which turns into a perfect square, tangent squared. So we should let y over 9 be secant theta. And then what's dy?
9 secant theta tangent.
Yeah, good. 9 secant theta tangent theta. D theta. And our substitution y over 9 is secant implies also that y is 9 secant theta. So we're going to need all three of those to resubstitute for this integral here. So we have still out the 9 out front. Our square root then here is secant theta squared minus 1. Over y, which was 9 secant theta. And all of that times dy, which was 9 secant tangent. Any questions on that? It's been like, what, 5 days since we last met and did this, so it might not be terribly fresh. So now's the time to ask questions. Okay, and we'll simplify this. So let's cancel this, doesn't matter which ones, we'll cancel those two 9s. We'll cancel the secant theta, the secant theta. And then, so what are we left with? Yeah. D theta, are we missing anything?
9.
We're missing the other 9 up here. We could have canceled the other 9s, whatever. So 9 tangent squared theta d theta is what we get. So how do we integrate or find the antiderivative of tangent squared? No. I mean, it's we could say it's a reduction formula, but we didn't have to remember those.
So parts.
We could try by parts. I think there's an easier than use substitution. Yeah. So what happens when we change tangent squared into secant squared minus 1? Becomes much easier to integrate because we know the antiderivative of secant squared and of 1. So we have 9 times the quantity. Antiderivative of secant squared is tangent minus the antiderivative of 1, which is theta. And then, I don't know, if you want to keep track of constants, we get a constant of integration that will be multiplied by the 9, which will give us another constant. Okay, so there's our antiderivative, tangent theta minus theta, all times 9. And then to resubstitute in terms of x, we have to draw our triangle that relates theta and tangent together based on the original substitution that y over 9 was secant theta. So that's secant, which then makes the other side square root of y squared minus 81. And then that way we can get tangent. Okay, so tangent is the opposite side over the adjacent, y squared, square root of y squared minus 81 all over 9. And theta was what? The inverse secant of y over 9? Plus c. And then of course we have 9 times this thing and 9 times this thing. Any questions on that?
I forget, why did the theta become the inverse secant?
So theta was the inverse secant because secant of theta was y over 9, so we just take
Oh,
the
yeah,
inverse
yeah.
of both sides. Yeah. Okay, clean that up. Call it good. So that's it. If you've tried to check the derivative here, you know the derivative is going to involve two different terms. So if you're checking to see does the derivative of this function actually equal to my integrand, that could also require a little bit of work, a lot of work for some of them. I checked one the other day from 8.4, and it took a good 5 minutes to make sure that the derivative was what we started with. So although that's probably not practical to do, you do have that option, just to check. All right, so I feel all right with that example. Is that okay? I think we'll skip this last example. We've seen a similar one where we've done one like this where we completed the square using u substitution. The one that shows up in the homework that you have to complete the square is much simpler than this example. So I hope the one in your homework is pretty doable. Sorry, this is x plus 1 squared plus 36. So I'm pretty sure we did one like this already. So this one was similar to the one we did where we said, okay, well, we're going to let u equal to that quantity squared. Then du was dx. And then we said, well, if u is x plus 1, then u minus 1 is x. Top became 2u minus 1. Okay, so the one that we looked at previous to this was similar, and what we did from this step was we split that up, 2u over u squared plus 36 minus 1 over u squared plus 36. The 2u over u squared plus 36, that's logarithmic form, or u substitution. And then the 1 over u squared plus 36 is what? Like if it were, yeah, that's the inverse tangent. So maybe you remember that, maybe you don't.
How did the top become 2u minus 1?
Well, then if x is u minus 1, then 2x is 2u minus 2. And then we add 1 to both sides. So we have 2x plus 1. Let's see, yeah, and so from here, splitting this up yields an antiderivative that we can find, or from this step we could trig substitute as well. We could have trig subbed here with the 2x plus 1 over the square. It just becomes a little more nuanced. All right. I think I'll just well, I'll write the answer down, but I don't want to go too much further. The ln of x plus 1 squared plus 36. No absolute here because that expression is always positive. Minus 1/6 inverse tangent of x plus 1 over 6. Let's see. As I've said, I'm happy to go over any of these that we skip. If you're working them and having trouble, please ask. We'll talk about it through email, before class, whatever. I just don't want you to feel like you're getting cheated because we're skipping examples. All right. So, questions on trig sub? In 8.5, we're going to look at algebraic technique, more or less, that's useful for finding antiderivatives called partial fraction decomposition. So the partial fraction or decomposition is the process of taking apart a fraction instead of combining a fraction. So decomposing, taking apart, that's where the name comes from. If you have time in algebra classes, they talk about this. I don't think that we talk about it here in our algebra class, which is not applied to antiderivatives. It's just the process of taking apart a fraction. And so a couple of examples here. This first one, 4x squared plus x minus 5 all over x squared. You don't really need a partial fraction decomposition on that, because we could rewrite each term over on the numerator over x squared. So this becomes easier if we just split everything in up top over x squared. We have 4 plus 1 over x minus 5x to the negative 2. And so we can find the antiderivative of each one of those if we just simplify first. Something like 2x minus 1 over x squared minus 5x plus 6, on the other hand, is a little bit different. So here's where, here's something that we would use a partial fraction decomposition on. The way we see these in context is it's a polynomial over another polynomial. So how do we integrate rational functions is when partial fraction decomposition could be a strategy to find the antiderivative. So here's an example. We'll talk about the process in a minute. But if we had 3x over x squared plus 2x minus 8, that's difficult to integrate. But through the process of partial fractions, we can take apart that fraction into 1 over x minus 2 plus 2 over x plus 4. And then each one of those are easy to integrate. So what is the antiderivative of 1 over x minus 2? Right, yeah, ln of x minus 2, absolute x minus 2, plus 2 times ln absolute x plus 4. So we can also check here this, just to quickly verify that 1 over x minus 2 plus 2 over x plus 4. If we cross multiply here, we have 1 times x plus 4 plus 2 times x minus 2. So x plus 4 plus 2x minus 4 gives us 3x. So we see that when we combine these things, we get the desired result. Of course, the denominator here is the same, right? Because we have x minus 2 times x plus 4, which gives us this quadratic. So it's really all of this. We just kind of skip that part. So we're going to look at how we decompose a fraction so that we can integrate something easier. Before you do partial fractions, though, your rational function has to be in lowest terms, and it has to be a proper expression, meaning the degree of the numerator is smaller than the degree of the denominator. And we've seen a couple of integrals where the degree of the numerator was larger than the degree of the denominator. That's where we use long division, right? So if those aren't present, then we have to use long division to get them in that form. Okay. So we always want to start off trying to factor the denominator, because depending on how the denominator factors depends on how we proceed, or how we're going to break down the fraction. So there's 4 different types of denominators that we're going to look at, or that we can encounter. Simple linear, repeated linear, simple irreducible quadratics, and repeated irreducible quadratics. So this is corresponding to the denominator. We don't care what the numerator is. It doesn't dictate how we break the fraction down. So simple linear factors are like x plus 1, x, x minus 4, you know, those kinds of linear factors that aren't repeated. And then item 2 says repeated linear factors. So if we've got a factor of like x plus 1 cubed on the bottom, or x squared, etc. I mean, some of these can get pretty terrible pretty quick. But most of the ones that we focus on are pretty friendly. Simple irreducible quadratics. How do you know, if you're given a quadratic, how do you know the quadratic's irreducible?
It can't be reduced.
Yeah, exactly. It can't be reduced. Done. But how do we know if it can't be reduced? Kind of, yeah, on the right track. On the right track, how you're thinking of it, for sure. Okay, let me write down a couple. X squared plus x plus 1 is an irreducible quadratic. Other ones would be like x squared plus 1. You know, x squared plus 4, so forth. if you were asked to solve the equation x squared plus 1 equals to 0, what would your solutions be?
I have nothing.
Yeah, they're not real solutions, right? You get imaginary solutions. So that's how you know your quadratic's irreducible, is if it has imaginary zeros. And the quick way to do that is to look at the discriminant. Do y'all remember that, the discriminant? So the part under the radical in the quadratic formula. So if the quadratic's b squared minus 4ac is negative, you know you're going to end up taking the square root of a negative number, which gives you imaginary solutions, which means your quadratic is not factorable in the real number system. So it's irreducible if that's true. And then repeated irreducible are just, these things repeated. So like x squared plus x plus 1 squared, x squared plus 1 to the 4th, so on. So it's important to be able to identify, once you've factored the denominator, what factors are making up the denominator, because each one of those scenarios has a different setup. You can't have a combination of all four of them, but the way we break it down is dependent upon what kind of factors we're looking at. Yeah.
So you have like x squared plus 4. What would that be?
It's a x squared plus 4. That's an irreducible quadratic, because your solutions would be 2i, negative 2i.
What if you had something that was irreducible, but was a quadratic?
Like, what do you mean?
Those t squared. If you were like x squared minus 2x plus 4.
Yeah, you could factor that, I think, into two linear
So it'd be
factors.
two linears?
Yeah.
That's what you do? Okay.
Yeah, right. Yeah, so if you end up with a quadratic that factors, like, just really depends on the quadratic, but like x squared minus 5x plus 6, x minus 3 times x minus 2, we would just factor that denominator first and say, well, that's the factors of our denominator. They're two linear and they're not repeated. So we have two simple linear factors in the denominator. Yeah. Okay, so the method of, presented in your textbook anyways, like I said, depends on which ones you're dealing with. So this one here is the situation where we have x minus r1, x minus r2. So that's like x minus 1, x plus 2. These are all simple linear factors. So you can use A's if you want, but let's look at a specific example. For example, if we had, let's say we had 2x divided by x plus 1 times x minus 2 times x plus 4. Then we're going to set this up as, we're going to say that it's A over x plus 1 plus b over x minus 2 plus c over x plus 4. Or you can use A1, A2, AN like the textbook is using. So each simple linear factor needs to be over a constant. And then usually the issue or the difficulty here is once we've set this equation up, we have to solve for A, B, and C. repeated linear factors, maybe you can decipher this, maybe not, but you have to account for each power of that repeated linear factor. So for example, if we had 2x over x plus 1 cubed, we would have to break that apart by saying it's a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed. So you have to account for all powers of that. Again, a, b, and c are constants that we have to solve for here. So that's repeated linear factors, simple irreducible quadratic factors. I think that's pretty straightforward. This is our irreducible quadratic here. We have to put it over a linear function, ax plus b, and solve for a and b.
That's type 3.
Yeah, type 3. For example, let's see, 3x plus 4 over x squared plus x plus 1. We have to set that equal to ax plus b over the irreducible quadratic and solve for a and b. I mean, this one's pretty trivial, but just an example.
Would it be 3x?
Do what? Yeah. Yeah, it's 3x and 4.
Wouldn't that
So this one, yeah, is probably not a good example because partial fractions doesn't really help with it. And then your textbook didn't, I don't think, it didn't mention repeated irreducible quadratics. But we can mention that. Repeated irreducible quadratics. So again, I'll just do this. If we had like x squared plus x plus 1 squared, for instance, we would say that's ax plus b over that thing to the first power plus cx plus d over that squared. Similar to the way repeated linears factors work, but we don't really see any of those. So unfortunately, this is just something that you need to know, because there's no telling what the denominator is going to look like. So evaluate 3x plus 5 over x squared minus 4x minus 5. The first thing you should attempt to do is to factor the denominator. So we're going to rewrite this. It's the integral of 3x minus 5 over, we have factors of 5 to add to get 4. Okay, so we factor that.
Plus 5?
Huh? Oh, on top, yeah, thanks. On top, 3x plus 5. So we factor the denominator if we're able to, and then we say, well, I'm looking at two simple linear factors. So maybe off to the side here, we can do this. We've left enough room. Where did that go?
Plus.
Oh, yeah. All right, so we'll do this kind of side work to decompose the 3x plus 5 over that thing. Do that for now. So since it's simple linear, we're going to say that 3x plus 5 over x minus 5 times x plus 1 is equal to a over x minus 5 plus b over x plus 1. You don't have to worry about the signs. Just say it's a plus b plus c plus d. The signs will come out as we figure out what a and b are. And notice the choice of how we factored the denominator was just one of the possibilities, right? You could have factored this and said, well, the denominator factors as x plus 1 times x minus 5. And in that case, you might have said, well, it's a over x plus 1 plus b over x minus 5. So that's valid too. There's nothing wrong with that. But what you'll see is that there's a definite choice for the number that has to be above x minus 5, or unique choice, and a unique outcome for the number that has to be over x plus 1. So it doesn't matter how you have those written. You're still doing this process correctly. We would come up with the same two numbers. Does that make sense? So it's irrelevant of choice and how you order that. So then how do we solve this equation for a and b?
You multiply them all.
Right, we're going to clear the fractions. So we're going to multiply through both sides by x minus 5 times x plus 1. Okay, so then that'll give us 3x plus 5 over here equals to a times x plus 1 plus b times x minus 5. So that's always your first step. Once you set this up with your a, b's, and c's, you always clear the fractions by multiplying through by the denominator that shows up here, that was present in your integrand. That's always your lowest common. Typically, I should say. Okay, so there's an easy way to solve many of these, and then there's a more long-winded way to solve these. So we'll look at both of them. I don't know. I guess it's relative, so I'll just put it in quotations. The difficult way to solve for a and b is just to multiply all of that stuff out. We have 3x plus 5 equals to ax plus a plus bx minus 5b. And then you have to equate the respective terms. So we have an x term here with a and an x term here with b. We have to equate those two terms to the term over here on the left that involves x. So we have the fact that 3x is equal to ax plus bx. And so actually what that means is, we've got two like terms on the right. What this equation implies to us is that a plus b has to be equal to 3. Okay. And then we're going to equate the constant 5 with the constant a minus 5b. which, you know, that's explicit as it is. All right, so that's what we end up with. You end up with a system of equations that involve A and B. So you got to solve the system by either eliminating or by substitution. Do y'all remember solving systems? In algebra, you just kind of eliminated or substituted. In pre-calc, you probably saw matrix methods for doing that. Okay, so we have 3 equals A plus B. Choose just, you could solve for A or B in that one. So we could say that, let's call this equation 1 and equation 2. So from equation 1, 3 minus A is equal to B. And then we can plug this in equation 2. To get 5 is equal to A minus 5 times B, which we're calling 3 minus A. So now we've got a single equation with a single variable, A minus 15 plus 5A. So we have 6A equals to 21. Oh, 20, yeah. Sorry. 6A equals 20. And then so A is 20 over 6. Which is 10 over 3. So once we have A, since we just have a system of 2 unknowns, you have one unknown, you have the other. So we've got A, we can get B, because we have either or 1 or 2 to plug into to get B. So I think equation 1 is easier. So then we'll plug this into equation 1. We have 3 equals to A plus B. And we can use that equation to solve for B. So we've got 3 minus 10 thirds. We have 9 minus 10 thirds. So we have minus 1/3. Okay. Any questions on what we've done?
You said this is a long one, right?
Yeah, more or less. The more difficult of the two. The short way, or the easy way. The thing with the easy way, quote unquote, is it doesn't always work. When it works, it's easier. It might just completely fail altogether, or it might just work in part. We'll see an example where I can point that out. So let's go back up to what we had originally. We'll copy that. And that's what we are looking at solving for A and B. So notice here before we even like distribute anything, one, we can say let x equal to -1. Because if we let x equal to -1, then it completely eliminates the a times x plus 1 for us. So if x is equal to 1, we've got 3 times -1 plus 5. So we have 2 equals to, this is 0, plus -1 plus 5, -6b. So if -6b is equal to 2, that's going to mean that b is -1/3. Okay, and the other thing we need to do is let x equal 5. So the b part goes away. So we've got 15 plus 5 on the left, we get 20. Then we have a times 5 plus 1, so we have 6a. And then the b, of course, is 0. So 6a is 20, that means a is 10/3. So that's the shorter way. Can you think about or anticipate a scenario where that wouldn't work? If not, it wouldn't fully work at all, or it might just work in part. So yeah, it wouldn't necessarily depend on the A, B, C, D, E, F, G stuff.
If they're the
When
same.
you're,
If they're the same, right? Like if you have like repeated linear factors, and we broke this up, it was like a over x plus 1 plus b over x plus 1 squared, right? Then you would say that this is a times x plus 1 squared plus b times x plus 1 equals whatever, we didn't specify. But let's say that was equal to, I don't know, 2x plus 1, right? If we said let x equal -1, you eliminate both a and b, and it doesn't give you any information. So that's one situation where the shorter way wouldn't work. So there are limitations to that. You might have to reserve the rest of this space. So either way, you've got your A and you've got your B. So we need to go back up now, 10/3 and -1/3. We need to go back up to this stage where we had to figure out what A and B were. And since it's taking up enough space, just write it here. So that's 10/3 and -1/3. I think I'll move all that down too. All right, so we're gonna go down here. I guess I didn't know to copy. And so what we've determined is how to decompose 3x minus 5 over that quadratic. So we had a over x minus 5, which was 10/3 over x minus 5, plus b over x plus 1. So the idea is now that those things are easy to integrate. So what's the antiderivative of 10 thirds over x to minus 5? Yeah, so that's just, a 10 thirds is a constant. And pull out. So 1 over x minus 5, the antiderivative, that's already in logarithmic form. Or if you need to, again, use substitution. Same thing for the second, minus 1/3 ln absolute x plus 1. Any questions on that? So typically when you look at antiderivative, you might, like we did in the past with quadratics, especially, we said, well, I can complete the square on the bottom, then you substitute, then split that up. Like that's, I don't know, it could be a tedious process, I guess. Not like partial fractions isn't a tedious process. But when we look at that, we say, well, it's not a square plus 1 or a square minus 1, right? So then trig substitution wouldn't be a viable option here. You could say, well, can I write it as 3x plus 5 times x squared minus 4x minus 5 to the negative 1, and then try integration by parts with that. We have two algebraic functions. But those are pretty much the only options when we have polynomials over polynomials. Like multiplying by a form of 1 isn't gonna help simplify that expression any more than it already is. Yeah.
So if it was like 2x plus 5 instead on top, could it help to like subtract 1 from the top and then make a new fraction? Where it's 1 over x squared minus 4x minus 5? Or would that just make you do another decomp for the other part?
Not quite sure I follow. If this were 2x plus 5?
Yeah.
Okay, so then what would you do from there?
You subtract 1 from there, and then you add 1, but you put it in a separate fraction.
So subtract 1 and add 1?
1 over x squared minus 4x minus.
Okay, so then you're talking about what if we had 2x plus 4 over this?
Then it's just a natural log. Oh,
Yeah.
it's negative though. Yeah, no.
Mhm.
Yeah, subtract.
Yeah, this, like adding in 0 is also an option for some of these too.
Okay.
Yeah, because this is, well, how would you do that?
Yeah, you'd have to do it with it decomp.
Yeah, so you would for this one, would it still have to be partial fraction decomposition?
Yeah.
This one though is in logarithmic form, so.
Except it doesn't work, but yeah. Okay.
But I mean, I wouldn't rule that out. Like adding in 0 in a certain way can be beneficial with, yeah, can be beneficial with rational functions too. I think that's it. So we're pressed for time, so we're gonna skip this one. It's similar to the first example. I'll write the answer down. 3 ln absolute x plus 1. And then seeing the answer, 5 times the natural log absolute x minus 2 plus c. So seeing the answer, you can almost see how everything breaks down, right? You can see how the denominator factors, you can see what a and b are going to be. All right. right then. So example 3, we've got repeated linear factors. So maybe we can just leave some space here. Our partial fraction here, we'll say that x squared over x plus 1 quantity cubed. How would we break that down?
Powers.
By powers, so it would look like a over x plus 1, then what?
B over X plus 1 squared.
Okay, then we account for the square with another constant, b over x plus 1 quantity squared. And then what?
C over X plus 1.
Yeah, another constant over the quantity cubed. We'll come back up when we're done. So here's an example where the shorter version doesn't work because all A, B, and C involve the x plus 1. But nonetheless, we're multiplying through by x plus 1 quantity cubed to get rid of the fractions. So we just have, we just have x squared on the left. We have a times what?
X plus 1.
X plus 1 squared plus b times, we just have x plus 1 for b, b times x plus 1 plus c. So actually, since we ended up getting rid of the factor involving x attached to c, in part we could use the shortcut method, but from here, if we let x equal -1, a and b go away and we can solve for c. We still have to solve for a and b. So then we need to expand this out. X squared plus 1. It gives us ax squared plus 2a x plus a. And we have plus bx plus b plus our c. Excuse me. And then we just equate like terms. So if you want to think about the left-hand side, shoot this over. Really what we're looking at on the left-hand side is x squared plus 0x plus 0. When we equate the x squared term, it's just the a. So we're going to equate that to that. So we have x squared equals to ax squared, which means that what? A equals 1, right? Okay. We'll equate the x terms, 2ax and bx, with the 0x. Which means that 2a plus b, 0x, which means that 2a plus b has to equal 0. Is everybody all right with what we're doing? Okay. So we already have a, so we have a equals 1. If 2 times a plus b equals 0, that allows us to solve for b. So b is -2. And then our constants equating 0 to a plus b plus c. So this one worked out pretty nicely. Some of the ones that have a, b, and c in it, you basically have a system of three equations and 3 unknowns. So it's like this 3x4 matrix that you have to solve. A lot of times just like substituting or eliminating can get you there as well.
In this specific type, well, C always be by itself.
Yeah, in this type of one, right? Yeah. Yep. Okay, we have A, we have B, we can solve for C. -2 for B plus C. We have -1, C equals 1. All right, and we need to plug those back in for A, B, and C up here. So we have 1 over x plus 1 minus 2 over x plus 1 squared plus 1 over x plus 1 cubed. I guess we'll write -2. Anybody have any questions? Okay, so this breaks down as how we have it. We have -2 rule of 1 over x plus 1 squared dx plus 1 over x plus 1 cubed. It's a little bit easier to work with than what we had originally. All right, so how are the last two terms then, or how are we going to find the antiderivative of those? Yeah, both of those are u substitutions. So u equals to x plus 1 here. And then whatever we'll call this a v substitution, just so it's not the same. Okay. The first one is already in logarithm form, or you can use another u substitution if you need to. So that's just ln absolute x plus 1. Might have to run out of room. And this is -2 times the antiderivative of 1 over u squared, or u to the -2. So I ran out of room. That's negative 2u to the negative 2 du, and this is u to the negative 3 du. So that's u to the negative 1 over negative 1, so we've got a positive 2. We'll write this out. 2 times u to the negative 1, so u was x plus 1. 2u to the negative 1, and then this, of course, u to the negative 2 over negative 2. So that's just negative 1/2. Sorry, that should be v to the negative 2 plus c. But that's the idea now that these things are easier to integrate. And that's our result. All right. Anybody have any questions? Do you have what you need? Can we move on? Or do you need a minute?
Just a second.
Sure. Ready? Okay, so we'll set up a couple of these. So the partial fraction decomposition for 2x plus 1 over x squared plus 121, what would that look like? I guess it's right there. Sure is. Okay, done. Okay, how about example 5? What would that look like if
A over x plus 3.
a over x plus 3?
Plus a over x plus a over x minus.
Okay, so is this can we reduce this quadratic?
Yeah. No.
So irreducible quadratic. We have to say that's bx plus c over this irreducible quadratic. Yeah.
So for the one above it, so would doing partial fraction decomposition does not help with this problem?
No, because you would just end up with a equals 2 and b equals 1, and then you're right back where you started from. So you'd split. You could split this up though. You could say that that's 2x over x squared plus 121 plus 1 over x squared plus 121. So how would we take the antiderivative of this thing?
That's just natural.
Yeah, that's already a log form. How would we take the antiderivative of 1 over x squared plus 121?
Is it tan?
Yeah, that's inverse tangent. So the ones that are over just a single irreducible quadratic, if you've got a linear over a quadratic irreducible, then you just split it up. One's a u substitution, the other is a arctangent,
So
typically.
would the same thing happen with number 5, with the second half?
Right. And so the same thing happens to the bx plus c over the x squared plus 9. In the practice of integrating this stuff, once you have b and c, you break that up in the exact same way. The bx over the quadratic is a u substitution. The c is a inverse tangent. Okay. All right, then what would number 6 look like? Whatever we have up top.
We'll just put
Yeah, just put 1 in. If that tickles your fancy, go ahead. Could be any numerator, though. Anybody want to take a stab at that?
A over x
A over x, yeah, simple linear.
plus e over x plus 1
Another simple linear.
this is the extra credit.
plus cx plus d over x squared plus 4 plus
Yeah, you're gonna be talking for a while.
ex plus f
EX plus F
over x squared plus 4 squared.
over x squared plus 4 squared.
And then you have gx plus h
I don't remember.
over x squared plus 4 cubed.
Over x squared. So all of those are taking care of the repeated irreducible quadratic, x squared plus 4.
Plus ix plus j over x plus 2. Kx plus L over x squared, or over x plus 2 squared.
Squared. All right, yeah. Pretty close. Do we need the ix plus j over the x squared x plus 2?
Well, it's gonna come out to the same thing.
Yeah, so since the x plus 2 is a simple repeated linear, yeah, you almost had that. So we would just say it's I over x plus 2 plus j over x plus 2 squared. Thanks, Patrick. Appreciate it. So we don't see stuff like that, but you very well could have that as a scenario. You know, something like that, you would end up with putting that into a computer, I think. I mean, it would take so long to do by hand. The equations
Oh my
one, two.
god. Wait, yeah, my calculator.
Yeah. But anyhow, it just kind of gives us an idea of how multiple things would break down. Okay. All right, so sorry for the delay. We'll take a break and then come back. We've got 2 more examples here in 8.5.
Damn. Came back right in your fucking beat. Oh, yeah.
Start swimming, brother.
Yeah.
How was it?
So I enjoyed it for a while, sleeping in and whatnot, but I'm just so far behind now.
Times
Around there. So yeah, not too bad.
Yeah.
I'll take it.
Yeah, that's fine.
Oh, just all freaking jazzed up.
I just like I can't. I'm like I'm done. Here's my test. So I have to make that one. Now I've learned basic testing. Don't slam head in coffee right now.
Yeah.
In your test.
Yeah.
Because 30 minutes later you're like.
Shaken violently.
Like, yeah, just like, I'm like, I felt like a junkie the whole time I was doing my tests. I'm just shaking like, oh no.
I walked to the testing center all prepared to do my physics exam first.
How did that go?
Physics exam wasn't even in there, so then I had to like shift gears and do calc right away. And then I wanted to take it physics later in the day. I had to go track down Fahey, get the test out there.
Yeah.
But that test actually went well, so.
The physics one?
Yeah. 95 on it.
Nice.
Yeah.
That was tough.
Yeah.
A lot of weird questions on that one. Threw me off for sure.
Yeah.
But
I'm gonna retake that test during the day.
It actually wasn't.
Yeah, he was like, hey,
take it with something different too.
definitely. I don't want to get caught up on like, leaves a lot for an entire day. Okay, I'm like, focused.
Yeah, I learn more on the homeworks than any time. That's why I just don't go to class anymore. I'll go to turn stuff in, but I just learn so much more doing the homework and problems in the book.
Yeah.
He's, well, everyone tells he's like really smart dude, but he's not the best teacher.
No.
Yeah, because like I got too confused when they first started talking about like the I-hats and J-hats.
Yeah.
The examples in the book, they started going through, but then they gave what they loved. They just gave it away. And I was like, well, you could just give me some practice doing some setups to figure it out. Don't just be like, well, you know, the angle's now 45. I'm just going to tell you now. You can plug all that stuff in. It doesn't help me solve this, but myself, you know, like, he just threw me way off, and I was confused for the rest of it.
Yeah. I found a YouTube channel that's really good at explaining those problems. They have like 300 different videos.
Yeah, is it the Film Academy? Because I was watching some of it on that, and I was like, this is a little bit.
Khan Academy is good. This is a different one. It's like, I think it's like the organic chemistry.
I think I've heard of that.
Wait, you guys talking about this?
Yeah.
Is that where you're not going anymore? Because you can't get sidetracked?
Well, I
Learned
learned.
class period on random crap.
Yeah, I learned so much more on the homework, so I just do problems at home, and
Okay, cool, so it's not just me.
no, it's I hate his lectures, and
Yeah.
they just make me more confused.
Yeah,
So,
yeah, okay. But you're using Organic Chemist, the YouTube series?
yeah,
Sweet, me too, awesome.
yeah, it's really helpful. Yeah.
Write that down.
Yeah, it's a great series. He's like two different playlists for the same, some different videos. But
Yeah, I figured if I take it during the day, then if that teacher, whatever new teacher I have, they're just like abstract and just all over the place, then I could at least set up a study group
yeah.
with other people. Be like, all right, guys, let's learn what we should learn during the lesson.
Yeah, exactly. Yeah, the organic chemistry too. This is the. Yeah. Find it. Really helpful. Really, just oversimplifies things. It's really nice.
Yeah, his class reminds me of before I moved out here. Another college out in Arizona, and I was doing chemistry track
Yeah.
for my transfer. So I was taking intermediate chemistry, or whatever you want to call it, basically. And that one was kind of similar. You go to the lecture, and the lecture didn't really have that much to do with the homework.
Yeah.
So I was sort of lost the whole time there, because then you'd be like, all right, now, you'd start putting equations up on the board.
Oh, because actually.
But it is the same thing where they wanted you to basically learn it yourself and then show up to class and if you had questions about it.
Which is great. I feel like his exam was the same way though. It's just like nothing like the problems at home. In my opinion.
Yeah. That's not fun. Yeah, hopefully there's more options. I have a reminder on my calendar.
You've done
Like
like
if it was like,
I'm done.
I got kind of forced into doing all the
Like I did.
night classes. And then
Yeah.
you want to go into a wait list.
And like I did this.
I signed up for not again, I'm gonna
Why
number
did
one.
Why did they choose to do this?
I was thinking this might be a little too.
Our calc.
I know it was like a calc.
That's a lot.
Like the Powell rule
So,
for derivatives, all the way to like,
I figured maybe, maybe I'll do like an
which is
SI.
whack. It's just like, what if you graph things, but instead of X and Y, you have degrees and
Wait, actually, when I do transfer
And like it matters when
Going
the
to
solver is
solvers.
You take a Coke? Yeah.
It like gets off on writing like really nervous questions and like that. People usually like get like around 95. It's like now I'm not like one.
I know.
I'm not like
Yeah.
And I like the
I have a
idea.
70
You
question
gave me a
homework.
great idea of like my startup should be trying to
Can't wait for
do
the next semester.
that light recapture. Instead of just falling down or blowing them up. Always have like.
Because of like
there.
random professors, I was like, there's
Grab it.
professors here, so maybe I should just give it. I'm just so bad at it. Like I feel like I will actually learn physics, but at least I'm gonna get like I can
Startup
my
to
career.
start the
I
next
can either.
business I wanna do.
I do wonder.
And I'm unsure if I want to go through all the trouble of semi-hard questions, like just be roughed up. Yeah, steroids and then just.
You can't put example problems on, like, I didn't check on the first two.
What if you look at it?
What it said,
It
said,
That's basically the
example
same.
problems.
I figured that's kind of what I really want to do.
They all
Feel
And then we get to bring all four of those.
Oh my god. That's a bad idea.
Wait, so do you not have
Then I
to,
might have a billionaire investor.
you just have to remember all of the equations?
And he even wrote equations for us.
Yeah, that's where they just start.
Exam.
Is SpaceX.
He like thought we were
Like a lot.
on there just.
Oh, was it?
It's the way they
I can't remember wrote it down,
test
but I think it was
that.
the
It's
same
semi
thing.
sort of the way that he's running
So-
SpaceX with testing. It's like I don't
Yeah, it's third law.
care about the
We're
work.
like done.
I
Been
want the
finished
electric
learning
car
shit since
out
like
on
2
the
classes
market,
ago.
regardless.
Yeah, we know.
You like
We don't
put
even
the
finish
answer out,
each
and
other
he's
There's
every
all
day.
this, he's getting all this like back.
And we had a class and he's like, you can do the
He's
homework
getting a
now.
bunch of backlash
And I'm
about
like,
it.
or you could like, I don't know, maybe take some more time.
Yeah, for all of his
That's
production
good.
facilities.
Right.
Or
So, like,
like
with
you
the
should
lab
see
and our
about
tests?
joining the
Or work for, like,
study group here. because
all
that's what
aerospace or
Tom
something.
said.
That'd be crazy.
I work right by them.
Yeah.
That guy.
That's cool.
And then
My
that's the next
friend's
super helpful.
mom,
You think it's good?
works there, and so I might.
It's rough for me.
might
Yeah.
I feel like he goes like he's just such a, like what he did in lab is what he does every day. Like he over-explains things really fun.
Yeah, get it.
You'll understand it, but it's like, you only go through like, so like basically what we do is each study days, we pick the like 3 to 4 hardest questions on the homework and then he'll like fully explain it. In like really weird ways, but it does help, but it's
Does he
like,
explain things in like a completely different way?
I could do without being in it,
Yeah.
but they kind of signed me up for it, and I was just like, oh, yeah. I like said a couple of last year, it's like something you have to go. But they find it really helpful.
don't know. To me, it's like whatever. He does give it, like, he adds conceptual thought to it, which is like.
They got like so many security cards, it's like my office is right next to them, so there's just security
I
cards
liked
running
it,
through
but I
our
felt
parking
like
lot, their
just
parking lot.
everything in like a very different way.
You have a gym card.
He really like doesn't like see he makes that like notice. He makes one of them like constantly.
So are your questions on the test, like,
I'm on
related
the
to stuff you do?
south.
Or do you
You know
fix it
those
so
new
it's
buildings they just built?
What we do in class
They
is
just
we
built the
like
second
prove
one.
the law of
Yeah, that's my
cosines using
office.
vectors.
Yeah.
Like,
It's
I
like
don't
the no,
understand what
there's no like examples
From
class.
Yeah.
It's just
Yeah,
like,
we have
like
like a
it's just
tractor out
notes.
there. Yeah.
And the homework's like medium, like level examples, and the test is like high level.
like the challenge problems.
So it's like we've seen like we know how to like use the like parts of the problems, but we haven't seen them like that.
Do you live over there, or how do you know that area?
I think it's mostly just like being able to
I
reason
live over there and I
through
work for Ball Corp.
Ball Corp?
You know,
Parent company.
basic concepts and like
Okay.
have the equation that you.
We're not
I
the sexy
think
part
I know
of spaces.
this.
I think the air.
Yeah, I mean it's usually like each chapter problem, it's like solve it this way, so it just comes down to like getting your
Yeah, it's
variables on your like
on,
sheet and
it's like right on the border of 128 watts.
Like
So there's
it's
a
gonna
couple
work.
buildings there.
Yeah, because one question on our test was the like
It's on the corner.
right?
You're in Ball Corp.
It was like hard.
I think you're closer to
First one, the first one.
Yeah.
I wasn't just
Like meters times.
so stupid.
freaking-
I was like, where
So
is
on
I was like, why are we doing
the
this?
southwest side,
I should have
right
done
behind Jeffco Airport right there.
so like on
Some buildings in there.
Yeah.
Right next to the Westport complex.
Are you by, 100?
we do use
I
those
take out
equations in a lot of
the ice
ways.
and the Circle Court complex, which is like right up here by that Jeffco Academy.
It's just 3D reflector.
Yeah, it's all across 36 from the other campus.
The other, okay.
Yeah, so there's, you got Jeffco Airport, you've got 128 in Lodz, you've got BCH, which is headquartered in
all the
aerospace.
shop cards.
And right across the street from them is another. Hangars. The other side of the airport is the PRC complex.
Okay, I'm on the other side. Right by that. Yeah, I'm the south side.
Yes.
Captured your break conversation on
That's not one.
video. My bad. Let's see, yeah. We'll look at this one, because it was directly related to what we were just talking about. So, let's see, we'll leave some space. Whoa. Okay. More space. We'll do 18 over x plus 3. X squared plus 9. So we did that in example 5. We set that up as a over x plus 3 plus bx plus c over x squared plus 9. Okay. And then multiplying through x plus 3, x squared plus 9 on both sides, we have 18 equals to a times x squared plus 9 plus bx plus c. It's two terms times x plus 3. So we could say let x equal -3. That would eliminate b and c and allow us to solve for a. But we still need to solve for b and c. So either way, if you go that route, you still have to set up the longer approach. to figure out what B and C are. So we'll have AX 18 equals AX squared plus 9A plus we have BX squared plus 3BX plus CX plus 3C. So do you want to go ahead and do the shortcut to figure out what A is,
Yes.
and then use this equation to figure out what B and C are? There's nothing we can plug in x squared plus 9 to get rid of. So if x is -3, we've got 18 equals to -3 squared plus 9. So we have 9 plus 9 times A. Again, B and C are gone because it's multiplied by 0. So that tells us that A is 1. So that, I mean, that can for sure help or simplify the process. Yeah, we'll just write this out. So we have our x squared terms. No x squared term on the left, so we have a plus b equals to 0. Our x terms also equals 0, so 3b plus c. B plus C equals 0. And our constants, 9a plus 3c has to equal the constant 18. All right, so that's the system that we would come up with. Whether we did the shortcut or not, the shortcut just helps us because we know A, which gives us B. Since A is equal to 1, we have B equals -1 from this first equation. And if B is -1, we have -3 plus C has to be 0 from our second equation, which means C has to equal 3. The same result, 1, -1, and 3 would have came out if we solved that system of 3 equations and 3 unknowns. But I think if you can use the shortcut to get one variable, it'll definitely make that solving the system a lot easier. 1, -1, and 3. Okay, does anyone have any questions on that? So we're going to put those back in place up here. A is 1. B is -1. And C is 3. So there's our decomposition of 18 over x plus 3 times x squared plus 9. All right. So that was kind of like our side work here. So the first one's log form. The second one, we've said that we have to break this up. We have to look at it as negative x over x squared plus 9 and 3 over x squared plus 9. Just go ahead and split all of these up. The middle one, then, if we had a 2 up here, we need this 1/2 out here. So that's now in log form as well. So we've got the natural log, absolute value of x plus 3. We got minus 1/2, natural log, absolute value of x squared plus 9. Since x squared plus 9 is always positive, and technically we wouldn't need these here. So if you want to have them, that's fine. If not, also fine. Plus, what's the antiderivative of the far right term?
1/3
Right. This whole thing. The antiderivative. That's 1/3 inverse tangent of x over 9, or sorry, x over 3. So the 3 out front times the 1/3 goes away. We just have inverse tangent of x over 3. Let's see.
Wait, don't you pull out a 9th though, so you get 1/3 out front?
For the last one?
Yeah.
Yeah, I mean that would be the trig, like the trig substitution route for that. If we pull out a 9 from the bottom.
Yeah, if you pull out a 9 from the bottom, isn't that how you get x over 3 whole thing squared plus 1?
Yeah. So if you pull out a 9 from the bottom, you have that over here. You have x over 3 squared plus 1.
And isn't that arc?
Yeah, that's still arctangent.
So don't you have a 1/3 out front?
No, because the formula's for the integral of
'cause
1
you use,
over x squared plus a squared. If we're writing it in this form, that's to say we're going to let x over 3 be tangent of theta for that. We're just following this formula for the inverse tangent. So that one's 1 over a arctangent x over a.
Okay.
So that's really the one we're following, is this one. But yeah, you certainly can do the inverse trig antiderivatives with trig substitution. And we saw that like in our, I think, second example with the one being inverse sine. Okay. All right, any other questions on that example? All right. Last example. What do we need to do here? Long division. The degree of the numerator is greater than the degree of the denominator. So this is an improper rational function. So we have to take all of this and do long division. So we long division first before we even start thinking about partial fractions. So we're dividing a cubed by a square. We should definitely end up with a linear quotient, and we'll check out what the remainder is. So we've got a 2x to multiply here, so that we get 2x cubed. 2x times x is 2x squared. And 2x times negative 6 minus 12x. So don't forget to subtract the entire thing. So we've got 0, we've got x squared minus 2x squared. And then we've got a 6x plus 12x. And bring down the 7. And start the process over. Oh yeah, thank you. 6x plus 7. Okay. X squared and negative x squared. So we need a negative 1. Negative x squared. Negative x. Positive 6. We'll subtract all of that. 0, 6x plus x, 7 minus 6. So there aren't any more terms left over. The thing that we're looking at, the 7x minus 1, is a less degree than the thing we're dividing by.
Plus 1.
So,
7x
yeah, plus 1.
Now we're
Thanks.
7x plus 1 over the thing on the
Right. So then we're going to say based off of long division, then we'll rewrite this. So 2x cubed plus x squared minus 6x plus 7 all over our quadratic is equal to 2x minus 1 plus our remainder over the divisor. And that's the thing we actually want to work with, since it's now a proper expression. So then we need to integrate 2x minus 1 plus 7x plus 1 over x squared plus x minus 6 dx. So the 2x minus 1, that's fine. It's this piece right here, the remainder over the divisor, that we need partial fraction decomposition for. Does anyone have any questions on where we're at? Does it all make sense? We handle these? All right, so this one is a reducible quadratic. So this is a simple linear 7x plus 1 over two simple linear terms. So I'll leave this as another exercise for you. But we've got x squared minus x plus 3 natural log absolute value of x minus 2 plus 4 times the natural log of the absolute value of x plus 3. And of course, those are coming from our partial fractions. Okay, so the last section in chapter 8 is 8.9 that deals with improper integrals. Also attached to our unit, though, we have 9.1 and 9.3 as well. So 2 sections from chapter 9 make up material that's on our exam as well, your quiz and your homework. But this is the last section in in chapter 8. So we're looking at improper integrals, and there's 2 types of improper integrals. One is when the interval of integration is infinite, and the other is when the integrand is unbound over the interval of integration. So what we mean by an infinite region is something to the effect of, if, let's say we had to integrate from 1 to infinity of the function 1 over x dx. So, what is that area? Is it finite or is it infinite? And the integrand is unbound on the interval. Could be something like the integral from 0 to 1, the function 1 over x dx. No, I didn't do that justice. Quite. Okay. So something like that. What is this area? So it turns out that some of these are, as we would expect, infinite, but maybe as you wouldn't expect, some of those things are actually finite. How this is developed or how these things are computed are, we look at those limits here with 1 over x. As we get closer and closer to 0, that's a vertical asymptote for the function 1 over x. So we have to look at that in the sense of a limit. On the far left, what happens as we get closer and closer to 0 from the right-hand side? For the integral from 1 to infinity, we have to look at the limit as some value approaches infinity on the antiderivative. So either way we go with either situation, limits are involved. So we need to do a review of limits at infinity and infinite limits. Really, these things you should be able to calculate almost instantly. So what is the limit as x approaches 3 from the right of x plus 2 over x minus 3?
Right?
From the 3 from the right,
Infinity.
it's infinity, right? So we're approaching through values that are slightly larger than 3. The denominator is approaching 0, but through values that are positive, right? Because we're approaching slightly larger than 3. So the denominator is approaching 0, it's positive, and the numerator is approaching 2. So anytime you have a finite number over a denominator that's getting smaller and smaller, your quotient gets larger and larger. So I don't know, just however we're going to indicate. Some people just write SP for small positive on the bottom. But that's the idea of this type of limit. Since we're approaching a vertical asymptote, it's going to be infinity or negative infinity. We just have to figure out which one. Okay, part B, what's the limit as x approaches infinity of x plus 2 over x minus 3? 1, right? That's horizontal asymptote situation, right? Leading term over leading term, x over x is 1. How about C? Infinity, leading term over leading term is x squared over x, which simplifies to x. Are those vaguely familiar? How about D? 0. Numerator's fixed, the denominator's getting larger and larger, so your quotient gets smaller and smaller. Example E. 0, again, numerator's fixed, denominator's getting larger and larger, quotient's getting smaller and smaller. F. Infinity. Come back to G. H. Negative infinity, because we have negative 3 times infinity cubed. So that's negative infinity. And I? 3/4. I heard 3/4, I heard 1. What do y'all think? 3/4? 1? That's what I heard first. But is it 3/4? Okay. How about G?
No, it's negative 0.
We're approaching values that are slightly smaller than 4, but on the bottom we're taking numbers slightly smaller than 4 and subtracting them from 4. So this the numerator approaches 2, denominator approaches 0, but through negative values, so small negative numbers. 2 over a small negative number is a negative large number. So if these are a little bit foreign to you, you might want to look in our textbook. I think chapters 2.5, 2.4 and 2.5. But limits like this are crucial in this section because they come up in every single one. Yeah.
Are we gonna deal with indeterminate forms?
Yeah. So you got to remember also L'Hopital's rule. This is in our textbook in 4.7. I believe. Maybe. I don't know. But the straightforward cases is where we have a 0 over 0 or infinity over infinity. F of A and G of A are 0 over 0. So this is the case for 0 over 0. Case for infinity over infinity, it's the same approach. Take the derivative of the numerator divided by the derivative of the denominator. So don't get it confused with the quotient rule. If you also remember with L'Hopital's, though, there were those 3 related indeterminate forms, right? There was 0 times infinity, there was infinity minus infinity, and there were those powers. It was 1 to the infinity, 0 to the infinity, and infinity to the 0. So, yeah, we actually have a couple of examples here. So find the limit for theta approaching pi over 2 cosine squared over sine minus 1. So just like with any other limit, you want to figure out what it is. If I try to evaluate this directly and it turns out to be something like 2 over 0, we can determine that value. If it's 0 over 2, if it's 5 over infinity, like all of those we can determine the limits. The only ones we can't determine limits for are these ones that L'Hopital's address, the 0 over 0 or infinity over infinity. So unfortunately, that one's 0 over 0. So, you know, instead of, we could try to like factor or use identities or whatever, but the main idea is that if it's indeterminate form 0 over 0, then just apply L'Hopital's rule to it. So that's going to be shorthand for this is equivalent to this limit by L'Hopital's rule. So L'Hopital's rule has been applied. That's the limit as theta approaches pi over 2. We take the derivative of the top. What's the derivative of cosine squared?
Wait, derivative.
2 cosine sine theta, yeah. So the derivative of cosine squared is 2 cosine times sine. Derivative of sine is cosine. Derivative of -1 is 0. So can we compute the limit as theta approaches pi over 2 of 2 sine theta? Yeah. No. Well, yeah, negative on top. Yeah, because the derivative of cosine here is negative sine. So wherever that negative goes. The point is that gives the derivative of the top and bottom. Remember, sometimes you have to apply this rule more than once, depending on what you end up with. But in this instance, it does give us something that we can compute. Limit as theta approaches pi over 2. We have -2 sine theta. So what do we get? -2. Okay. All right, how about e to the x over x squared as x approaches infinity? Right, so we get infinity over infinity from just directly substituting infinity over infinity, which is not 1. Don't call those things 1. It's just meaning, remember, the numerator is getting larger and larger, the denominator is getting larger and larger. Really, in situations like that with infinity, it's also helpful to know, like, at what rate are they getting larger and larger, right? So e to the x grows much more rapidly than x squared does, right? So e to the x approaches infinity much more rapidly. What would we expect this to limit to be if that were the case? Right, because the numerator is getting larger and larger and larger much more rapidly than the denominator is getting larger and larger. Okay, so let's see if that's actually valid. Since it is infinity over infinity, then L'Hopital's rule, limit as x approaches infinity, derivative of e to the x over derivative of x squared. So we have to do it again because it's still infinity over infinity. So one more application. Derivative of the top divided by the derivative of the bottom. As x approaches infinity, e to the x over 2 approaches infinity, yeah. All right. So we do have another example through this section. I think it's one of the latter examples where we get a related indeterminate form to infinity over infinity or 0 over 0. So we will see that, but it's probably a good thing to review that. Okay. So this idea that we talk about here in this paragraph, it carries over to chapter 11 when we talk about sequences and series. So if we evaluate an improper integral and it comes out to be not equal to a real number, meaning infinity or negative infinity, then we say that that integral is divergent. Or we say it diverges. If it is equal to a real number, then we call the integral convergent. So to evaluate these things, you need to look at the function and determine, well, what's causing the issue. The issue here is because the upper bound is going off to infinity. So the way we handle that, and we're going to stick with just the convention from the fundamental theorem of calculus, how it's written, integral from a to b, so f of x dx. It really doesn't matter what we call the improper portion of that integral. So since it's the upper limit, we'll call that b. We'll say we're going to look at the integral from 1 to b of 1 over x dx. But we have to compute the limit as b approaches infinity, whatever that happens to be. So we're going to compute the antiderivative via the fundamental theorem of calculus first. And then once we have the antiderivative plugged in the bounds, then we'll compute the limit. Okay, so we'll go here. So what is the antiderivative of 1 over x? Yeah, so that was natural log. We have the limit. We have natural log absolute value of x evaluated from 1 to b. So we'll plug that in. Limit as b approaches infinity. We got natural log absolute value of b minus natural log of 1. So as b approaches infinity, natural log of 1 is 0. As b approaches infinity, symbolically what we're looking at is the natural log of infinity. It's positive, so as the argument approaches infinity, the natural log approaches what? Infinity.
But it's small.
So that integral is, we would say it diverges. It's infinity. It's not a real number. The integral diverges. Meaning, or I guess another interpretation, anyhow, 1 over x So it just means that this area from 1, the area under the curve in the x-axis, is infinite. That's another way to interpret that. I mean, I don't know if that's obvious or not, but I don't think it is obvious. All of this area is infinite. Some of them are finite. And then so that's where you get the paradox of things like I can have a finite volume but an infinite surface area. Like I can come up with this object that I can fill up with water, but I could never paint its surface. Right? So that's kind of how some of these paradoxes arise. All right, similar example here. This is the second case, or the second type of situation. So if you take this function 1 over x from 1 to infinity, you revolve it around the x-axis, you compute the volume of that figure, it's finite. If you compute the surface area of that revolution, it's infinite. So if we have time, we can look at that, but The issue with this one here is that 0 is not in the domain of the integrand. So, excuse me. Since that's the problem, whatever you want to call this, though, this is our lower limit of integration. We need to call it A or T something. Sorry. So that's for our lower limit of integration to 1 of 1 over x dx. But we need to compute the limit as a approaches 0. Excuse me. From what direction? We're approaching 0 from the plus side, from the right. Because our excuse me, our interval is from 0 to 1. We can only approach 0 from the right. Just a minor technicality there. Sorry. Okay. So similar antiderivative, different limit. So we have the limit as a approaches 0 from the right. Natural log absolute value of x evaluated from a to 1. We've got a similar thing happening here. Compute the antiderivative first. The limit is always going to be the last thing that you apply here. So we have the limit of here the natural log of 1 minus the natural log of a. Absolute value of a. We technically don't need that because we're approaching 0 from the right. Those are all positive. So you have the limit as a approaches 0 from the right. 0 minus natural log of a. So what would that limit be? Well, as a approaches 0, what does the natural log approach? Negative infinity, but we have a negative in front of that. So it's actually approaching negative infinity. Again, at this point, it's just a technicality. Infinity or negative infinity doesn't matter. Still means you have an integral that diverges. But the area above the axis or below. So we also have a divergent integral there as well. Again, I'll just, instead of graphing this, we'll just draw it. So we'll just say that's 1. So that area is also infinite. Are there any questions on what we're doing here? So how about the integral from negative infinity to negative 1 of 1 over x squared? So you see the issue is the negative infinity on the lower limit of integration. So we're just going to call that a or t or whatever. Doesn't really matter. To to -1 of 1 over x squared dx. And then we're computing the limit as a approaches negative infinity. Antiderivative of 1 over x squared. Oops. Gives us -1 over x. Evaluated from a to 1. Plug in the bounds before you compute the limit. So we have -1 over 1 rather. F of b minus f of a.
It's supposed to be evaluated from A to -1.
Yeah, a to -1. Thanks. Well, I'm just erase this. Well, I guess it would turn into plus. Okay. So
Wouldn't it be -1 over
well, you would have, yeah, let's see. You have -1 over -1, and then you have a minus a -1 over a. So that would be a minus -1 over a, that second one. So as a approaches negative infinity, what is this limit equal to?
1?
It equals to 1 because 1 over a approaches 0. This approaches 0. So we actually now have an integral that converges. Which is, kind of weird. 1 over x diverged, 1 over x squared converges. Well, I guess we could take that off, but either way, it's symmetric, so. Let's look at the positive side since it's symmetric. That graph compared to the graph of 1 over x might give you a little bit of indication as to, why the graph in blue, 1 over x diverges out towards infinity, but 1 over x squared in red converges towards infinity. So it really just has to do with the rate. Like how quickly are these things 1 over x? How fast are they getting smaller and smaller? Versus 1 over x squared, how fast is that getting smaller and smaller? So this idea of how quickly something gets smaller and smaller, does it get smaller and smaller, directly plays into the chapter 11 when we talk about sequences and series. So it is a concept that we revisit, and it's crucial to certain portions of calculus. I guess we can leave it there. I'll see y'all Thursday.
Someone's on campus.
Yeah. You're like doctor.
I was like, no, that's
My friend's taking this class and they're like behind.
I saw you one time. I don't really